All right. As I said for this class, you guys have looked at at this point, you've looked at your calculator, and you've seen that, as I said, this whole rest of this course, we're going to learn all those statistics that are under that stat button, on your calc, under tests. Now the catch is this. There's a lot of them, but they're very similar. Really, there's two main ones, and I'm going to show you as soon as this pops up. Under stat, when we go to tests, which is where we're going for the rest, notice that most of this stuff is either a t-test or a z-test. Those are your main tests. So z-test, t-test, we'll learn that. 2 sample z, 2 sample t, we'll learn that. 1 proportion z, 2 proportion z, we'll learn that. Z interval, T interval. T interval is what we're going to cover today. 2 sample Z, 2 sample T, 1 proportion Z, 2 proportion Z. Intervals. So far we've only hit the intervals. Okay? We're going to get into that. It's chi-square test. That's a chi-square goodness of fit. That's a third statistic we'll learn. F we won't do. Linear regression, t-test. We'll talk about what that is. We'll get into that. You guys know what linear regression is. Linear regression t-interval. We will not do ANOVA. The other things we won't do in this class. We won't do the z-test, and we won't do the 2 sample z-test. We'll do the t-test and 2 sample t. We'll do a 1 proportion z, a 2 proportion z. We really won't do a z-interval, but we'll do the t-interval. So we won't use every one of them. But the catch is this. What to do in what place at what time and why. And that's the hardest part. Okay? So, that's the wrong one. Not this one. These are the things that you need to know, or these are the justifications, or this is the explanation as to why. This is the proof if you're going to create a confidence interval using the t statistic, this is your justification as to why. And it's 3 things. Independent, random, and normal. Those are the 3 things. Independent, random, and normal. Okay? Things that you want to go with independence. This is the key idea for independence. We're sampling without replacement. We call it less than 10%. And if the sample is less than 10%, we would say that independent sampling is justified. Or we're going to say, is a sample. Sometimes they're going to say, hey, this was done. It was taken randomly from a group of blah, 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 blah. And as long as that sample is less than 10% of the overall population, then this condition is met. You got to have all 3 of these. Okay? Random sampling, we've talked about that quite a bit. You need to find it in the context of the problem to see if it has been randomized. Because we can't apply anything about that normal curve or that t-curve if it's not random. And we don't do non-random statistics in this class. The other thing is to check for normality. And you guys should know at this point, if we're talking about a t, where it's a mean problem, greater than or equal to 30 is our magic number for a large enough sample. Because if we have greater than or equal to 30, then the central limit theorem will apply. And I know that my sample will be randomly distributed, or it will behave normal. So we've covered that greater than or equal to 30 before. These are the big 3, random, independent, and normal. Okay? Those 3 conditions will show up again when we get into hypothesis testing. These conditions are what you'll check for hypothesis testing. These conditions are what you check for confidence intervals. Confidence intervals and hypothesis tests go hand in hand. Okay? We all right with those big 3? We did this 100 min, 70 inches. Yes. You guys still need to copy that down?
Yeah.
Sorry.
So also you must apply the
It's justification as to why you're going to apply that t-confidence interval. It's saying like, because the sample is greater than or equal to 30, because I have sampled randomly, and because that sample is less than 10% of my population, I can use this formula for the t-confidence interval, which is x bar plus or minus t created times estimate. Yeah, it will fit. It's going to be a reasonable estimate because of it. And if we're doing 95%, we know that we're still going to miss 5% of the time, on average. Again, I highly recommend you get a flashcard, make these, I would like random on one side of that flashcard and then what random means, normal on one side of the flashcard and what normal means, independent and what independent means on the flashcards. You need to get these three. Okay? Is it okay to move now? We did this one really quickly in class. All right, but I'm going to do another one. Here we got a quick estimate the true average test scores taken from a sample of 41 test scores. The sample has a mean of 710 and a standard deviation from that sample of 25. So it just wants us to do the confidence interval here. It doesn't say what our confidence interval is, so what are we going to use if it's not listed? 95%. And again, 95% is our happy median. 99% we're going to have a super wide interval. We're going to be super accurate, but it's not going to give us that much information because it's going to be really wide. 90% will be a tighter interval, but we'll miss 10% of the time. 95% is our happy median that we're not missing all the time, but we're relatively small in our interval width. So that's why that's the rule of thumb. Conditions here. We now need to satisfy our three conditions. Let's see, and that's independent, random, and normal. Well, is normality okay here? Yeah. Normal, so sample, so I would say sample is normal, n, which is the number sampled, is greater than or equal to 30. And greater than or equal to 30, that means that we can apply, so I'll just say central limit theorem. Are you guys okay with me abbreviating it? Central limit theorem applies. Okay. It's just really thick. Central limit theorem applies.
Hey, watch the video.
Yeah.
So do you have to have this in your answer, or is this just?
These are the things you're going to start needing for your work. Random. Does it say in the context of this problem if this sample was random?
No.
It doesn't. So here's what we need to do. We're going to assume this is a random sample. Because if it's not given to us, and we don't state that we're making assumptions, then whoever reads our work will say you're full of, and it doesn't, your work is invalid. Okay? So now that we've said, well, we've assumed this, so because I've assumed it, then my work is justified. Because I'm making this assumption. Independent? Well, we need to kind of say independence is justified if it's less than 10% of our population. Agreed? So I would need to say something like population must be greater than or equal to 410. Does that make sense?
Oh, yeah. I was looking at 70 and I was like,
Our population must be greater than 410 people. Why? Because 41 is what we sampled, and our sample has to be less than 10% of that population in order to meet this justification for independence. So I've made some assumptions here. These 41 scores must come out of a population that's out of 410 test scores or more. And not only must I have a population of more than 410, I must have sampled those scores, pulled them out of that hat with thorough mixing or randomizing, putting all the kids in a name, giving them all a number, and hitting my calculator for random number, right? Is that okay? Like, do I need to cover randomization again? Okay. So, those are the big three. Notice how we're writing about this. And we're going to get this into then writing, like right now, it's just kind of a very simple structured format. In fact, on the AP exam, you don't need to write in these big, beautiful paragraphs. On AP Stats, they like you to communicate what you're doing. And do it in the most efficient manner possible. Okay? I'll tell you what I have written on the board is probably a little too brief for the AP exam. For independence, I would say population must be greater than or equal to 410 because otherwise the 10% rule is not effective. Or we cannot assume that independence is met. Random, I need to, that one pretty much speaks for itself. I assume this sample, this is a random sample. That's saying, hey, it wasn't listed in the problem, so I'm going to assume that. Normality, we've got normality. That's an easy one. Our sample is greater than or equal to 30, so therefore we can apply the central limit theorem. I would also write out the word central limit theorem. I wouldn't write CLT. Okay? They don't want long, big, beautiful paragraphs. They want you to communicate what's happening, and then they want you to show the dry formula. Show the dry formula. Show the formula with the correct things plugged in the correct place, and then you can go to your calc. So x bar in this problem was 710. Plus or minus, we'll come back and get the t-crit. S of x is 25. Divided by the square root of 41. We need to get the t-crit. We're doing 95% confidence. We have n minus 1 degrees of freedom, which is 40 degrees of freedom. Oops. Which means I need to inverse t. 95 is 0.025, comma, 40. You can pull this right off your formula sheet as well. You'll see at the very bottom, I showed you guys who have to use formula sheet, 95% confidence, and 40, that's actual value on your formula sheet. I don't know what this t-crit is. 2.021? Sounds good. 2.021. There you go. That's what they expect in the form of work. At this point, you can go to your calc. You don't have to show all your work from here. And it's going to be under stat, tests. This is not a t-test. This is a t-interval. Notice there's two things that say data and stats. This time you're going to plug in stats. Stats is when you have the actual information. In this case, our mean was, I forget what the mean was, 710?
Yeah, 710.
Standard deviation was 25, and our number of samples was 41. We want the 95% confidence interval. And like I said, in this class, the calculator is going to do most of the work for you. Notice on these confidence intervals, your calculator has to do some time thinking. It's one of the few times with these calcs you see them actually have to do a lot of crunching. Good question? We're going to talk about that today. We're going to get to data in just a sec, which means we're going to have to put the data into list 1, and then we're going to pull it from list 1. Yeah.
So on the AP plus intervals, do you want us to write all of the paper?
No.
So okay, so you're just gonna put the answers of T interval like that.
Yeah. We can go. This is all the work you need. There. Now I need to write the sentence interpreting it. But that's up to this point, that's all the work I need. Somebody asked me to show the calc again. It is from our main screen, stat, tests. You need to go down to the one that says T interval, which I believe is 8, yeah. T interval. We're pulling it from data. The question came up, when do we use data, when do we use stats? I'm going to talk about data in just a sec. Stats here, make sure that's hard. Get your information. We have a mean of 710, standard deviation of 25, 41 people in our sample, or 41 tests in our sample, and we want the 95% confidence level. Okay? And that gets our answer. Okay? Finish it up with your interpretation. We are 95% confident that the true mean of test scores can be found within 702.11 to 717.89. And you don't really need this next part, but I'm just going to write it to kind of make a point. Inclusive. And what I mean by inclusive is actually if you get a value of 702.11, that would still count. In this case, it's a greater than or equal to or a less than or equal to. Okay. And again, we have our 4 things that we're checking for context. We talk about our level. We put it into context. We're talking about the true. I see true mean. That's talking about the population again. It's not talking about my sample of test scores. It didn't tell us what this test score was. If it had been like SAT test scores or ACT test scores or any of those things, we would have had to get that in our conclusion. But it does. It just says test scores. So again, confidence level. True mean tells us we're talking about the population, not our sample, context of that population, and then listing the interval. And you don't have to have that inclusive. I'm just making a point that, hey, if we happen to get something at 702.11, it actually counts. Question? It's always inclusive. And I haven't really spoken to that. That's why you guys don't need to put it. But if you're putting things on a confidence interval, the rule of thumb is that it is inclusive. Okay? All right. Some questions. Or any questions on that last one before I go to this one? Sorry. Kind of went over it. Any questions? Because that's top to bottom there. Yeah.
So will we also have to include the independent variable in the
You do. You need this is, if this is an AP question, this is what you need. All of it is really your answer. You're going to be on an AP grade. On an AP grade, if you just write this and that, you're going to get like a 1 out of 4. Well, because all you've communicated in terms of understanding is that you know how to use your calculator and something that your teacher told you to memorize. And so it's worth a 1 out of 4. Think about, remember, it's demonstrating what you know. And what I want to do is justify. You guys know what this means or apply it. That's what the AP exam is, yeah.
Will it be not inclusive?
No, it's always inclusive. And like I said, I just hadn't spoken to it, which is why I put it down right now. You guys don't need to put that. It's assumed when you're talking about confidence intervals. The endpoints are inclusive.
Repeat the 44 for the
N minus 1 degrees of freedom, there's 41. N is 41. 41 minus 1 is 40. Okay? All right. 2 intervals. 92.268 to 97.732. The other interval is 90.222 to 99.778. That's for the true average resonant frequency in hertz for all tennis rackets of a certain type. Okay? So, first question. What is the value of the sample mean resonant frequency? And I'll give you guys some time to talk about this in your group. See if you guys can't come up with an answer for that, because I'll tell you that you do have the skills. How do people agree our confidence interval goes like this? Our confidence interval go like that? Okay. Well, this is a confidence interval, and this is a confidence interval. What do you know that's between them? What has to be between these two values? The x bar. What needs to be between these two values? X bar. How do you find something that is halfway between two values? Add them up and divide by 2. Wouldn't that give you, wait for this geometry word, the midpoint? And isn't that what x bar is? The midpoint? Because you took a value and you added something to it. You took a value and subtracted something to it. Just like when you have a parabola, algebra 1, a parabola and halfway to the vertex and halfway away from the vertex are your roots from plus or minus the square root minus b squared over 4ac. Trevor's like, whoa, I don't know what just happened.
So if you once you find the average of both the two intervals, do you add those together, or are they just two different?
They should be the same value. But they had better be.
Because they're the same.
Because
It's just different.
it's different confidence intervals. Yes, and how many people realize that x bar is the same thing here? Basically, we have the same sample, same standard deviation, same sample number. One of those is a confidence interval for a certain level, and one of them is confidence interval for another level. What's x bar here, by the way? 95. Next question. What's the margin of error? Can you find that?
Isn't
Isn't it the t crit times the same? No, that's
Yeah, but
isn't the error?
here's a tip. Take the information you have and apply it in a way that I haven't told you directly how to do.
95.
I got it.
Do you guys agree that the margin of error is B? B the thing that you add and subtract to your x bar in order to get the upward and lower? So if you have the mean and you have your interval, can you find B pretty easily? By the way, do you agree that you're going to have a different B value for here than you are here?
Yeah.
Okay. What are those values? 2.732?
Yeah.
What's the other one? I didn't do that one. 4.778? Okay. Again, do you notice how the math is very easy? This is, again, how you will see a multiple choice question on the AP exam. They'll give you this information, they'll give you this information, and then it'll say, what is the value of the sample mean resonant frequency? And there are going to be 4 choices, A through E. Yeah. How do you find B? You know that x bar is 95, which means 95 needs to be in the middle right there, and 95 needs to be in the middle right here. So just take that number, 99.778, subtract 95 from it, and that becomes your B value. Take 97.732, minus 95, that becomes your B value. Yeah.
We should just always use this second. I don't know.
Doesn't matter, these are plus or minus, but our margin of errors, we always represent as positive numbers.
Oh, so would you have four answers?
Yeah, technically that and that,
Oh, okay.
but like I said, remember we have plus or minus, so our B value or our margin of error is always represented as a positive number. We just report it as a positive. But we will be adding and subtracting that thing. So. Last question here. The confidence levels for one of them is 90%, the other is 99%. Which is which? That's applicable for Halloween. Which is which? Which one is 90%? Which one is 99%? And of course, how do you know it and why? Okay? So I'll let you guys talk in your groups for that for about a minute, and then we're going to move on. You're a 99%er. Justification being, on the 90%er, I'm going to capture that mean only about 90 times out of 100 on average, which means it's going to be tighter because I'm going to be missing more frequently, but it'll kind of be more, be tighter, be smaller. 90 to 99, that one's going to be wider because I'm going to miss less frequently. In fact, I'll only really miss that population mean about 1 time out of 100 on average. Does that make sense? Okay. We'll be good here. Yeah, we're good. Yeah. And what we're doing right now. All right. Closing out the chapter. What we need to do, 2 things. We're going to look at samples less than 30. We're going to look at samples when their n is less than 30. And we're going to figure out how many people we have to sample in order to get accurate, just like we did for the proportions. So, yeah, it's just a 9.3. You should agree with me right now that the skeletal box plot matches that distribution. Yes?
Yes.
Okay. No? Here's what we're doing. We got a data set that says preceding data, that data there is the cadence, which is strides per second for a sample of 20 randomly selected healthy American men. Okay? So I now have a data set. My data set is less than or equal to 30. I mean, it's less than 30 in this case. So my sample is not sufficiently large. So if we're looking through our big 3, which is independent, random, and normal, well, it does say random here. Randomly selected healthy American men. Well, I don't know if it's normal. Do we agree that we can't apply normality here because it's less than 30?
Yes.
Okay. Does it say independent? So we're going to have to assume independence, or can we make some sort of judgment here? Independence is justified when our sample is less than 10% of the population. How many did we sample here? 20. Out of the population of what?
Healthy American.
Healthy American men. I think we're less than 10% of that population. Oh, dear God, I hope there's more than 200 healthy American men in the United States. Yes, but not that small. So again, if I'm looking at talking about my requirements, we now need to say independence is justified. Sample of 20 is less than 10% of the population. So now I'm talking about my population. The population of healthy American men. Again, we hope it's reasonable. There's more than 200. Independence. Random is easy. random. All I need to do is say sample is this too dark for you guys? A random sample. So our sample is random, so we're good. We've got 2 out of the 3. Normality. Normality, we are less than 30. So, you can put it in the back.
Okay, and then first cans, we drive, and then since we're first, and the third period, first cans gets a peach party.
Third period?
Yep.
Alright.
Is it per capita, like, in other words, average per kids in class, or is it just total?
Right. Total.
You have
Well-
to get stats. You have to ask stats.
Well, it's not fair. If we compete against PE classes where there's 50 kids,
But they don't bring it.
and every kid brings in 3, that's 150. You guys, every kid brings in 3, we're less than 100. We're down by 50, if that's not the case.
Expecting 20 from each.
But who's gonna bring cans? Alright, okay, you got my 20?
So,
I wanna do that thing that
I haven't touched my.
were you in my class when we did that? That was awesome.
This stats class was on last year, and I was in that class.
Oh,
Back at the problem.
Sherbert?
Back at the range.
Yeah.
That was the same 2 years ago.
Our sample is less than 30. Here's what needs to happen. We can check to see if our sample is normally distributed. If our sample is normally distributed, we can apply the t-curve to it. Again, big connection piece here. If our sample is less than 30, but our sample is normally distributed, then we can apply the t-curve. How can we check to see if this sample is normally distributed? What? Rapid. Put it in your calculator. How would you check to see if it's normally distributed in your calculator? Put it into list 1.
Where's the list?
Oh my god.
Edit.
Put it into list 1. And I'm not going to put it into that. I'm just going to go to my calculator because I don't have time to put it into my. Oh, actually, I might. If I haven't put that up, I'll put it here.
0.95.
1.
0.92.
Never say, we'll never stop.
You got
We didn't need that.
Well, it's on my notes, so. You messed it up just
Is it 193?
6.95. Okay.
There
you go.
Wow.
I was already on the next
Wait, is this all one list? Yeah.
Oh.
If I give you my password, will you just discuss my phone? I'd much rather you do that instead of deny the comment. You have to change it. I'd much rather you discuss in my phone. Do you want it? Wait,
How do you determine
All right.
what, did you grab the 0.06 of the stripe?
This is stride lengths per second. So I would imagine strides per second.
I don't know if there's anything.
So it's how many strides they take in 1 second's time. Which I would imagine what they did is they took a distance of like say 30 meters, and then they timed to see how long it was, and then they divided by 30 strides per second. Or timed it for 30 seconds to see how long. All right. Now that we've got this data in list 1, the question becomes, how do I check to see if it's normal? Don't all jump at once at this one, by the way. Perhaps a box plot?
Oh, I was just about to say box plot.
Yeah.
Not even done. So long ago.
This was so long ago, I don't remember.
I was just there.
Oh, me, oh my.
How do you get there?
Wait, so I entered it, and then second.
Me, oh
Do you
my.
guys need me to show you how to create skeletal box plot again? Or a box plot?
Yeah, basically.
Go to stat plot.
And then you say that's all. Oh.
Turn it
Yeah,
on.
I've got that.
Go down to the one that looks like the modified box plot, because that will show outliers. Highlight that. Tell it to pull it from list 1. Exit out, and then zoom stat, which is zoom 9.
Mine looks cool.
So mine looks
Mine were on that.
Doesn't matter, it's arbitrary.
Can you reset my graph box?
Yeah. All right. Well, that's when we talk about trimming. Like we had. Well, go back that first slide. Oh, not this one. Might do it like that. Right.
So that's not normal.
This is not normal. That's skewed, isn't it? That's why I put that back at the beginning. And so if our data looked like that, then we would say you can't use it.
So basically, we're looking for a center block.
Yo.
When we can put the graph thingy you have on top of it, or can you just leave a box as well?
What's that?
Can you put the graph thingy in the screen that I had a little graph that made it look cute?
That looks like one's bigger than.
We're looking for approximately normal. That's all we're looking for. That?
Yeah, is there any way I can make graph about?
Any way you can what?
Make that graph thing out? Because mine looks like almost normal, and it's hard to tell.
For this problem, it should be almost normal. Yeah. We would say that this is good. Okay? You're looking for length of whiskers. You'd like to have them, in a perfect world, the median would be dead center. But the median's just a little bit off. That's okay. We're looking really for outliers and whisker lengths. That's what we're checking for normality. That is one way to check for normality. And we would say, at this point, I would show that, and I would say box plot is approximately normal.
So you have to do your box.
Yeah, you're going to need to draw the box plot because you need to provide justification as to why you're doing what you're doing. You don't need to. You can just sketch it like that. So now we've satisfied our normal because our sample is approximately normal, so that means we can apply the t-distribution. And that's x bar equal plus or minus t crit times s of x over the square root of n. Again, we've satisfied our big three. I want to show you another thing that can be used to apply normality. Okay? And it is this. It's really the only time we're going to use it. It is this one. So go over to this one. It's called a normal probability plot. a normal probability plot. And give your data from just list 1. Just list 1. It's called normal probability plot. It's the far right one. It's another reason to justify normality. So if you want to be great and ideal and perfect on your AP exam, you'll show both the skeletal plot and the normal probability plot. Okay? So toggle that, rezoom status, so zoom 9 that. Okay? Here's the deal. All you need to do on this normal probability plot, does it look like a line? Does it appear to be approximately linear?
Yeah.
If it's approximately linear, then you're good to go. Normality is justified. Okay? If you see things that pattern out or don't fall in a line, you can't apply it. So those are your 2. Yes?
Can you say that it's how dry now?
We don't want to, what you would say for justification here, you'd say something like this. You can just sketch it, and you can say, the scale doesn't matter on that, and you can just say normal probability plot is approximately linear, so normality is justified.
So you shouldn't say anything if you don't.
Yeah, but if you don't sketch it, you're going to get docked. You need to justify normality. This is one way to justify it. That is another way to justify it.
So you have
More and more frequently, these have been showing up. This is why I show it to you. You're looking for it to be approximately linear.
So you have to sketch each out.
You have to, yeah, rough sketches are fine.
Let's get it like that, or do we need like ask?
You know, scale does not matter at all on this one. Because actually what it's doing is normalizing the z-scores for every data point you have. There's actually 20 data points. And you got to have an equal number above and below because they average out to 0. All right. Notice that your justifications is just as big a deal, if not a bigger deal than the actual calculation itself, right? At this point, it's pretty easy. All you got to do is find the x bar, the t crit, standard deviation, and the square root of n. We knew in this case n's 20, correct? Okay. Wouldn't it be nice to have that value? Could I run one variable stats to get that value? Could. But there's got to be a better way. And today, for $9.99, go over to tests. And once again, we're doing a t-interval, correct? And this time, instead of inputting my stats, whatever I'm going to do, I'm going to input my data. From where will I input my data from? I don't know. How about list 1? We'll do the 95% confidence level. Hit calculate.
So do you have to write all
And I'm shocked to see that they tell me my X bar, my standard deviation, and
Me, oh my, I'm shocked.
what's that? Asking for 99 because I didn't read the slide.
That I don't know the rest.
So we need 99% confidence interval, not 99, not 95. To show your work for this, here's what you need, besides what I already wrote down.
Yeah.
Okay, at this point, the dry formula, and then this plugged in, so 0.9255, plus or minus, I got to come back and get the t-crit. That standard deviation is 0.0809, and square root of n is 20, and then inverse t, I'll pull it off the table. We have 19 degrees of freedom here, so I want 99% confidence, so that will be inverse t let's see, 0.01, so 0.005, comma, 19. And you said it was what?
2.861.
2.861. And then after you show the dry formula, the correct substitution, you can write your confidence interval down, and then you just need to write your sentence, which in this case is we are 99% confident that the true mean, what was this, cadence something? Stride per second for healthy American men. Strides per second in healthy American men can be found in the interval, and then you can just list the interval, 0.8737 to 0.977 to 0.977. And there you go, that's top to bottom.
And verse 2, where do you put it?
This is the one.
So getting that that problem is just data, you put your data, that so we put it in a calculation data,
Not stats. The first example I did today, I think we used stats because I gave you stuff. Give you a data table.
So they already give you something stats, but they give you a table.
Yep. Table's a little bit more involved. And the reason it is because you got to justify that normality because usually, inevitably, your sample's going to be less than 30. Okay?
So the question is only 9.3.
These 9, yeah, it's going to be mostly on 9.3. Actually, I think it's all going to be on 9.3. All right, the only thing that I want to look at now, sample size. What time are we out? 14 today? Okay. Sample size problems.
Is it due? Are we actually experiencing? I feel like
To guesstimate your sample size, what you need to do, you actually use the z-values. You use z to guesstimate because you don't, think about it. When we use the t, we're using the standard deviation from our sample. Agreed? Everybody agreed with what I'm saying right there? If I'm trying to figure out how many people I need to sample, I don't have the standard deviation from my sample. Does that make sense? So if I'm trying to estimate how many people to sample, I use my z. Okay? And I would say 90% of the time, they're going to tell you, in this course, they're going to tell you the population standard deviation. Okay? Oh,
That was a new goal.
I think it just overheated.
Yes.
too much stats.